Runge Kutta methods. We are still trying to approximate the solution for the initial value problem. Y prime equal to a function f xy, y at x0 equal to y0. Approximate the solution for this initial value problem. To start. So we know about the Euler's and improved Euler methods. So assume that we are in step n, we have xn, yn. So here's the idea for the Euler methods. This is the actual solution curve, y here. We are in the step where we have xn, yn. We want to predict xn plus 1, yn plus 1. And the Euler method said that we just use a point on this tangent line to approximate the next point. Xn plus 1, yn plus 1. So xn plus 1 is xn plus the step size 8. Yn plus 1 is yn plus, because this point is living on the tangent line, so the slope of the tangent line is y prime at this point. Y prime at this point, by the hypothesis, this is f xy. Slope is f xn yn and times the step size. So this is the Euler methods. And then we have the improved version. Now we have the Runge Kutta methods. So instead of just having this simple approximation here by this tangent line, here's what they do. So here you have yn minus yn plus 1 equal to this. We don't want that that simple. Runge Kutta methods say that yn plus 1 minus yn. We are trying to approximate yn plus 1 is y of xn plus 1 minus y of xn. We are in the step n. So this yn plus 1 is approximation for yn plus 1, and we have this now. This one, by the fundamental theorem of calculus, this is the integral from xn to xn plus 1 y prime of x dx. So this is just the integral. Integral of this will give us this. Now we know that xn plus 1 is xn plus 8. xn plus step size 8 of this term. Now we will use the Simpson rule to approximate this integral, and we use a simplest version of the Simpson rule. Simpson rules. And actually this is Simpson 1/3 rule, the simplest version of that. So here's this goes. If you have an integral like this, a, b, say f of x, or to make it different from that function f of x we have over here, I will use g of x dx. So if you learn calculus, you know that integral, this one is just the area under this curve, right, from between x, from a and b. So think about that, and there's many methods to approximate the area under the curve, and here's they use the Simpson rule. And the approximation is b over a, b minus a over 6 times g of a plus 4 times g of a plus b over 2 yn plus g of b. Yeah, so this is the Simpson rule. Now let us use Simpson rule for our integral. So this integral here, we approximate this by b minus a over 6, so 8 over 6 multiplies on these terms, right? Here you think of y prime h g, y prime at xn plus 4 times y prime at xn plus xn plus 8 over 2. Here you think of this a as xn, b xn plus 8, and then plus y prime at b, so y prime at xn plus 1, xn plus 1 here, xn plus 8. So this is our approximation for this integral. This is yn plus 1 minus yn. So now we have this formula 8 over 6 plus this. I will try to further split this one into 2. So we have yn plus 1 minus yn is approximated by this formula. Now we try to split the middle term further. Look at the middle terms, xn plus xn 2 times xn plus 8 divided by 2. So this one will be 2 cancel out, xn plus 8 over 2. So y prime xn plus 8 over 2. So this is the second terms. I just rewrite this first, and now I break this into 2 times this plus 2 times this, equal to 2 times this one plus 2 times this one. That's what they do for this method. Okay. So we still have 4 times this. Now this is what we can do. This term is good, 8 over 6, the step side over 6, y prime xn. So y prime xn we know xn is here, xn yn. Y prime at xn yn is actually the slope at this point. So this one, the first term, is the slope at this point. Yn, y prime xn is the slope at f xn yn. This is by the initial value problem. We know y prime equal to this, and we call this k1. Call this one k1. Now let's look at the second term, y prime at this one. So now we look at the Euler methods here. I draw at the point xn, yn, I draw the tangent line at this point. Instead of going full one step ahead, so the step side 8, I already do 8 over 2. So we have, say we are in this point, xn plus 8 over 2, and we have some values for y. Let me call it u n. Un xn s over 2 un. This point is living on this tangent line. So it satisfies the equation of the tangent line. This point is the Euler point when you use the step sign 8 over 2. Un is actually yn plus fxn yn times 8 over 2 equal to yn plus these terms we call it k1. So this is k1 times 8 over 2. This is un. So we have a new point right here, this point. At this point, we have a slope f of that point. Let me call the middle point, I call m1. Y prime at m1 equal to the slope at that point. So it's a slope at xn 8 over 2 un, which is this term. That is this slope of this m1. Now I call this slope k2. So we have k1 here, slope at the beginning, k2, the slope of this middle point. Let's look at this term. Now for this point, I want to approximate that a bit different from the previous point. Instead of using k1 as an estimation slope for un, I want to use k2 because we have it now. So we have the point, say un tilde, which is un plus, so instead of having k1, we have k2, 8 over 2. And the slope at that point, so un tilde is a bit different from un, so that we have a new point, m2. M2 is xn 8 over 2 un tilde. Un tilde is this point. That point is our m2. And the slope y prime at m2 will be f of this point. So by the initial value problem, we know the slope at this point. We call this one k3. This one will be our k3. And we'll use that to approximate the third term, k3. Now for the last term, for this last term, I will just do as the Euler method. I will go just full step ahead, xn plus 1. So at the point xn plus 1, yn plus 1 tilde. So xn plus 1 is xn plus a step sign 8. Yn plus 1 tilde is yn plus the slope times the step sign, and I use the slope k3, the one we just get. K3 times step sign 8. And the slope of this point will be the one we use to approximate the latter, y prime xn plus 1. Y prime xn plus 1 will be the slope at this point, xn yn tilde. So y prime n plus 1 f xn plus 8 y n plus 1 tilde is this one. This one we call k4, the last term. Now we have all from k1, k2, k3, k4. We are good to approximate this one. So all together yn plus 1 minus yn plus 1 minus yn equal to this 8 over 6 times this, which is 8 over 6 k1 plus 2 k2 plus 2 k3 plus k4. We have the approximation yn plus 1 will be approximated by yn plus 8 over 6 times this. This formula is the Runge-Kutta method. So in summary, you only need to remember this. Xn plus 1 is xn plus step size 8, yn plus 1 equal to this. And to remember k1 to k4, you have k1 equal to the slope f xn yn. That's a step we are currently in. K2 is a slope f at xn go half step further, and then this is yn plus half step using slope at k1. K3 will be exact same thing as here. Instead of slope k1, use slope k2. And the last term, k4, is full step f xn plus 8. So xn plus 8 and yn full step, remember that. So multiply s, and the slope we use here is k3, the most recent one. So altogether, this is a formula for the Runge-Kutta method. For the error, absolute value of the error, white xn minus yn is bounded from above by a constant times f4 methods, Runge-Kutta methods, this right, RK4, fourth order Runge-Kutta. So is it much better than Euler's and improved Euler methods? The Euler's methods, the error term is bounded from above by c times 8. The improved version of Euler method, c times s squared, and in this case we have c times s fourth. Yeah. So here's the formula.